Hi everybody, thank you for joining us. My name is Ori Peretz, I am Principal Security Researcher at Microsoft. With me, Mayan and Vladimir. They are researchers as well in our team, and we did some research on Codesys v3, and we're going to share it today. So what we're going to talk today is, first of all, overview about Codesys, what the motivation of this research and why we conduct it, OT artifacts and OT forensics, how it's mean and what's need to be done to achieve it, some binary reverse engineering and firmware analysis, and the vulnerabilities we found during the research, some works that we did to be able to extract the artifacts needed, memory layout reconstruction, so we discuss about it, and open source tools that's available and we published, and Q&A. So a little bit about Codesys. Codesys is a SDK that's widely used and being able to execute in various architects, CPUs, and operating systems. Now, when we talk about various, this is a glimpse of the industries that are being used: Codesys, automotive, energy, chip and building automations, and each of any vendor that's in the slide have a line of products that's running over Codesys. Now, you probably understand that if it's a framework that's so widely used, probably is interesting for attackers. Now, we discussed about operating systems. So QNX, VxWorks, Windows embedded in Linux is part of the operating system being supported by Codesys SDK, and of course, a lot of CPUs, ARM, PowerPC, MIPS, and so on. Now, when we come to examine this research, we start with how much devices of Codesys available online. This is a heat map of available devices online, and you can say that it is a lot. Now, the motivation that we came from is to try to understand how we take the forensics way of doing forensics in IT and try to implement it on OT. Now, the reason is that there is no common ground of forensics methodology to OT, and we know that during the years there was being highly rise in attacks on cybersecurity in IoT and OT. Specifically, each of any one of those attacks had some effects on OT devices, and each work that we did on the OT forensics artifact we extract are being examined against one of those attackers: Stuxnet, Indestroyer, Cosmic Energy, and so on. Now, the main things that we try to achieve is to be able to track third-party implementation of software that being delivered to the PLC, and might target the PLC. Now, when we discuss about the use case, and we start with a code of InController that is nation-state sponsored tool that target multiple ITS systems, and he had Codesys model that have the ability to scan, communicate, and logic modification. Now, why it's interesting to understand it? When logic modification is applied, you have the control of the PLC, and you can harm damage or harm lives. Now, as I mentioned in the beginning, Codesys SDK is widely used, and therefore ICS, it's interesting to nation states because everybody run it. There is dozens of vulnerabilities on those devices that need to be patched, and there is no OT forensics tools that allow you as an IT guy or an OT that's interested in security in terms of cybersecurity to imply. Now, if we want to take apart what is OT forensics, we need to start with ICE 611 313. This is the standardization industry for execution PLC programs. Now, every one of those languages, ST and FDB and IL and SFC and LD, are the same language with different representations. We aim and focus in this research in the LD, which is ladder logic. Ladder logic is resembled to a ladder, as you can see here, and it's executed in ranks. Now, every command that executes on the PLC is determined by the input and the output that's being executed. So the input will be the contacts, and the output will be the coil, and every time that's the rule that's amplified and the rules that apply and execute, this will be execute the next rank, and it's sequentially running. Now, another important things to understand is how PLC projects look like. So we have the hardware, as I mentioned before, a lot of hardware supported. We have the OS, as I mentioned before as well, a lot of OS being supported, and then you have the application. Now the application has to have one task, and one task have to have POU. Now POU is the programming organized unit. This is the unit that actually execute when the task being called. You can have a lot of tasks, and they can share vulnerability variables between them, but you need to remember that there is a task, the task have program, and the program is executed. Now, how it's been, how we take it from here. So if we take a look in the IT world, we know that timestamp outliers are interesting for us from various reasons, but in our case, we want to make sure that we understand what the time that the code actually executed, actually modified, sorry, and we want to be able to verify the author information. If the author is not aligned with the regular use, it might be suspicious. We want to make sure that we understand the task uses and what makes them execute and what triggers them. We want to make sure that we're able to highlight the codes that use malware, network capabilities, sorry. The network capabilities probably will be point us to interesting logics that might be being used by attacker, or misconfigurations that's being applied, and we want to take a look at it and understand if it's applied correctly. And the last one is online-offline project comparison. We know that the code that actually executed on the PLC is not necessarily the one that we have on the engineering station. We know that we have the IDEs and the comparison tool of them, but we know that if the IDE is compromised, we don't have the ability to count on that. So we are trying to achieve it offline, like without being executed through the IDE. Mayan, thank you.
Thank you, Ori. So now we are going to speak about the reverse engineering work we've done to be able to extract forensics artifacts out of the PLC project compiled binary. So let me introduce you to the research timeline, consisting of all the phases that we went through this research. So the first one is going to be the project parsing, which was basically writing an example project, compile it, and then start looking for interesting data types and structures to be able to extract them and to see what we have over there. But this phase wasn't enough for us, because we saw that we need to do some dynamic analysis of the PLC firmware file. So we wanted to see exactly how the PLC code is being executed in the PLC. Doing that, we also found some vulnerabilities in the COTIS version 3 protocol, and we disclosed them with the COTIS organization. After gathering all of this information, we were able to collect all the information we need to automatically extract data from the compiled binary. And then we were able to build a plugin supporting the COTIS version 3 protocol, and to extract forensics artifacts and be able to investigate a PLC project file. So let's begin with the project parsing section. So to begin with, we use the PLC that is based on the CodeSys version 3 protocol. And we wanted to be able to write an example project and start examining the compiled binary of it. So we downloaded the CodeSys version 3 development environment. And then we use some tools such as IDA and the O10 editor to be able to look at the actual binary and the disassembled code of the compiled project. All right, so at the beginning, we knew that the PLC is based on the ARM CPU. So with a little endian byte in order. So we were able to open it in IDA and start looking for data structures. After that, we gained some initial insights of the data. So we have the header of the file that has the application name, GUID, and some pointers. We have the footer of the file, which exists at the end of the file. And it has the project name, which is different from the application name. It has the version, the build date time, author name, description, and more information. And we quickly noticed that the rest of the file consists of the actual project data. And it's split by something called protocol tags. So protocol tags in ICS are values, mostly integer values, that represent data types. So if I'm going to encounter a specific tag, it's going to follow by specific data type. So that's it. And after that, we were able to spot gaps, to spot the actual components we want to look for. So we want to look for tasks that we know that drive the whole execution of the project, of the PLC. And we want to look for the code sections, which are the POUs, the Program Organizational Units. And for that, we have a lot of work to do. So let's begin. So we want to be able to reconstruct the whole call execution flow. So this is the to-do list we're going to follow. And we're going to look for the following components. The POUs, which are the actual code section written by the OT engineer. We have the functions, which are CodeSys functions that can be used throughout the project. We have tasks that are basically the main function of the code. We want to look for them too. And eventually, we want to be able to write some automatic code that will do that. So we will have to look for the protocol tags mapping because we want to parse the different sections within the file. And we will look for the application entry point because we want to know where the application actually begins to execute. So let's start with the POUs. Now, for that example, we wrote a project with specific POU code section. And from the left, you can see the STL code. So the logic is very simple. We have if statement, if some function, then assign some hard-coded value to a variable, and then call some other POU. So we need to be able to identify this code section in the compiled binary. So from the right, you can see the disassembled code we found in IDA. And we were able to find a POU because of the hard-coded value. So this is great. We found, we are able to find the code section in the compiled binary, but we still need to be able to fix the jumps to other POU in the compiled file. So how we're going to do that? So again, we have the example. And from the left, you can see the jump to the other POU, example 1 POU. And from the right, you can see the disassembled code and how the jump is being done after the compilation. We have a specific pointer offset that is being loaded. And then this pointer is going to be loaded to the PC register, which is the program counter register, which is going to be the next instruction that is going to be loaded by the CPU. So this is how the jump to the POU is being done. This is the pointer offset. And how we are going to know that this specific pointer offset related to the POU that we have. So we are going to use something called the symbol table, so just a quick brief. A symbol table is a data structure that consists of essential identifiers such as variables, function names, and function pointers. So by looking for this specific pointer offset, we were able to find the entry in the symbol table of this specific POU. So from the left, we have the jump and from the right, we have the entry in the symbol table related to our code section. So now we found all the POUs and the jumps. So this is done. And now let's patch the calls to the functions. Let's go back to our example, and let's see that we have a call to if is first mass cycle function. So in CodeSys, this function means, is this the first cycle of this specific task running on the POU? And we want to be able to patch that call. So we looked for this function name in IDA, and we encountered a data structure that eventually was the function symbol table. So again, this table consists of all the mapping of the function names to their pointer offset, because the jump is being done in a similar manner. And now we are able to patch all the calls to functions within the compiled binary. So this part is done as well. Now let's search for the tasks. So we know that tasks are like main functions, and they drive the whole execution of the project. And each project must have at least one task. So we want to spot tasks in the compiled binary. So what we did was writing an example project with specific task that has some specific code, but this code is going to call other POU. And now, because we know that we can patch POU calls, we are now able to spot tasks in the compiled binary. So this is great for us, but we're not done, because we know that tasks are a special object that also has some parameters that are related to them. They have names, they have types, they have priority, they have their cycle time, and more essential information. But we saw that static analysis is not enough for us to extract this information, and we have to do dynamic analysis. So this part is not done yet. And let's go back to our mission. We want to be able to extract forensics artifacts. We want to build a nice call graph of the project. And we know we can take all the information that we found, the tasks, the code sections, used libraries, and so on. But to do that, we need to write something that will do this for us automatically. And for that, we have to know the mapping of the protocol tags that exist in the compiled binary. So we have to look for the tags and also the entry point, but doing static analysis of the binary is not enough, and we have to look in the PLC firmware. So what we're going to do is look at how the PLC firmware actually executes the project, how it loads all the tags and the data structures. Then we're going to take this mapping, all the pointers, the tags, and write some code that will extract for us all the information we still left with. And then we're going to build a forensics framework that will do this for us. So with that being said, let's start the firmware analysis part.
Thank you. Hi all. So I'll talk today about the firmware analysis, the reverse engineering, and what we found while doing this. And so basically what we found was the protocol workflow, the project execution, the found vulnerabilities. And so after opening the binaries of the firmware, we successfully understood how all of it works together and found some problems as well. And so we started by opening this little guy, the playground, we call it. And I used Beanwork to open the project to find the different files that actually executes on this PLC by Wego. The interesting files located in the ImageSysOS directory. And using strings, we found fastly what are the files that are relevant to the actual firmware that contain CodeSys components. And so after finding those files, we imported them into IDA and tried to open them. And we needed to understand which flavor, which exactly architecture we're executing on. And so for that, we opened the PFC and found that the CPU is SPIR680, and from that we found its little arm. Now, do you remember this image that contains the 55 city magic? After searching for that one in the binary, we find a number of references to it. And so from here, we had a foothold to find relevant things for the tags we're searching for. Now, in order to successfully open the binary, we wrote some IDA Python custom project. And basically, it helped us to open the binary better, to understand, to find the right function names, use logs and suffixes and inheritance, logic to rename better. And basically, we found out that in the end of the file, there is a reference table, which is basically a double D word that points to a string. And then after a double D word, it points to a method. And from that, you can rename the methods based on the reference table. And so after doing all of this, we successfully opened in IDA the file and found all of those components. Now, the binary, the compiled binary firmware, it's a sum of different components that execute different logics for different services. There are a few interesting here. However, the one that was most interesting for us to understand how the project executes, how the compiled ST project executes on the PLC was the component app, which have a number of different logics that it manages and does, and upload download files, delete boot projects, which boot project is a project that's being executed when the PLC starts running. And so after finding this component, we successfully opened all its flow and found the relevant tags that we wanted to find before. And so we have successfully found application tags. And now another interesting thing is the application entry point, and this is we understood from the execution of the IC task, which will be used, I'll talk a little bit later. And so while going over component application code, we found code that looks like that. We can see here the btag reader get content, which basically will copy from the hreader the imported tag, the tag we received over the internet, and write its contents into the PPBY area. And the size of it will be stored in the PBI area size. Now, after that, we can see that a memcopy is being executed from the PBI area onto the new AB area to add. And so we can see that this variable being casted into int, which is 4 bytes long, but the memcopy will copy the amount of payload that's been passed. And so obviously, it's a stack-based overflow because the new AB area is stack variable. And so we found a lot more vulnerabilities in this order, in this type. Some of them DOS, some of them RCs. But now the interesting part is how we can exploit this, right? How we can do something cool with that. And so if you basically will send long enough payload, it will crash the PLC, and we have some crash log like that. And which is nice, but it's not exactly what we're after. We want to actually execute code from that. We want to achieve RC, remote code execution. And so for that, we need to handle two mitigations. We need to bypass those. We have the ACLR and the DEP. ACLR, as you know, is the address space layout randomization, and the DEP is data execution prevention. Now, to bypass ACLR, we use very classic technique, which Rob Gadget will just found some pieces of code that we can use to jump and execute the wanted opcodes we want. And for bypassing the DEP, we needed to actually look into the inner workings of the IC task, which is the execution point of codices. And so it just happens that IC task has segments that have the execution, read and write primitives on them, and it falls that the stack segment of the component that's been executing falls onto that segment. And so basically, it means if we successfully write some code onto the stack, we can execute it. And so from here, also from the IC task inner workings, we understood how we can find the entry point to the execution of the ST. Now, after all of that, let's present the actual RC, POC, the exploit, how it looks. Basically, first of all, we have some noise data to put on the stack. Then we have the registers values that we will use later in the shellcode. And then we have the PC, specifically where we want to jump. And here we want to use the BLX gadget that will allow us to execute code from the stack, because we have execution permission there. And then we have the actual shellcode, which in this case will be returned to libc, because specifically on the presented PLC, the libc is located in a custom location, and it won't be randomized, and then we can use the return to libc attack here. And specifically, the exploit will reboot the PLC. And here is a presentation of the exploit. I'll start. Yeah. Okay, so first of all, we can see the execution of the exploit. It's sending some packets over the network to the PLC. And then successfully executed. This is the PuTTY connection to the PLC. We can see here it's been disconnected. And then we can see the lights of the PLC wigging off and starting on again. And this is the actual POC that allows us to execute code remotely on a Wego PFC. Wonderful. And so, as I said before, the understanding of the IC task and the whole extra research we've done here to find and exploit the vulnerabilities allows to find the application tags and the application's entry point. And this is it. Thank you.
All right. So Nat, with that being said, we can now start to rebuild the memory layout of the compiled project. This is here. We are going to use the found tags, the entry point, and start to extract all the information that we were looking for. So, quick brief again. Now we know that the protocols tags have specific mapping that we can use. By using them, we can parse now each section, for example, the symbol table, and then we can write some automatic code that will extract all of that at once. So what we're going to do now is to read a file, read each tag, and parse the data structure according to its role. And then we're going to parse the whole project file and assemble all the components and extract the artifacts that we need. So we know that we gather essential information. We gather the entry point, the code sections, the tasks, and so on. And we can start building the memory layout of the file. But we're still missing the tasks configuration, which are crucial information that we must extract. So for that, we need to do some dynamic analysis. And what we did was building an ARM simulator. So let's go over all the sections. The first step was implementing a state machine, which basically is following the ARM opcode, the registers handling, and the stack. It is based on the Capstone Python module, and it's based on the ARM little endian, but it can be easily modified to a big endian binding order. And after implementing this, we were able to simulate some essential functions. So we simulated the memcopy function to be able to see exactly what values are being loaded to the memory. We also simulated the codesys function named sysSetUpTasks because this function actually set up the tasks loaded to the PLC, and it gets a pointer to the task array. And next, we have the codesys function named sysRTSCycle2, which is also another important codesys function because it has a pointer. This function gets a pointer to each task in the PLC project, and it also executes the actual logic that is going to be executed on the PLC for each task. So with all of these phases, we were now able to extract the actual configuration of each task and build the call graph of the project. So the to-do list is now all done, and Herlinda is happy. And now let's move on to the building of the codesys version 3 protocol for the open source tool.
Okay, so we almost finished. Now we need to be able to take everything and wrap it up into something that's actually being useful. Now to do so, we have the following. Okay, so the first thing that we need to do is to be able to extract the data that we just mentioned, which is the PRG, which is the app that actually executed on the PLC. What we are doing is connected to the PLC via the codesys v3 protocol, download the file under $PLC logic $, and take the file, the project file that's and with the prefix .app. Now this is the project that's interesting for us, the files that we just analyzed. Now we have to analyze the project. What we do, we extract all the tags, we parse the known sections, we patch found symbols, we use our simulator to support the tasks information and dump the data to some CSV so we can show it later. Now, how it looks like in the framework? So, first of all, the project metadata. As you can see, there is some elevator name project with the build of the project and the name of the author and the time that can be used. We have the network capabilities that's being used by the protocol. In this case, it's used Schneider Electric some Modbus, if I'm correct wrong. And you have tasks. This is, for example, the data of the interval and the time and the cycle, and all of it seems messy, but if you are an OT engineer, you easily understand it, and if you try to go over, it's well documented in the CodeSys SDK. Now, we want to be able to create a call graph, so you start here, and you have the ability to understand where the important functions might be. And the last one is the online-offline comparison between the projects that we just downloaded and the projects that we received from the application engineer station. So we have the ability to compare those files and understand if there is some problems. Now, where you can find everything, so the tool is called IC Spectro, and it's open source tool that we published a while ago that support various protocols. In this case, this lecture is of CodeSys, but it supports other vendors. To be able to understand the CSVs that's been, CVs that's been discussed, you have a white paper and an active tool to understand if you're vulnerable for them. And if you're interested in the advisories of those CVs, you can find them there. Now, how we take this insight and protect our organization? We want to be able to take a vulnerability management. We want to have the ability to take OT forensics capability and secure and resilient our OT environment. To do so, here are a few takeaways that we recommend you to consider. So the first of all is proper OT network hygiene. So segment your network, make sure that you have some behavior anomaly detection on your network, because most of the attacks on OT devices are network-based, and you will probably want to establish a process that will be timely patch deployment and make sure that you are aligned with it. Now, the other thing is we are considered from supply chain attacks, so make sure that when you are use popular OT SDK, you are patch it accordingly, because as long as the SDK is commonly used, is more attractive to attackers, and probably will be used in the APTs. Make sure you have SBOMs to your devices, software bill of materials, and to be able to understand the third-party components, and make sure that you regularly update your PLCs. Now, another thing that we recommend to do is you can use ICS Spectro to take snapshot of your network and track changes. And we encourage you to deploy an incident response plan to specify specific to the IoT OT devices if you don't have yet. And the last but not least is to make sure that you request your vendors to follow the secure development practices, to make sure that if there is some problem in the PLC, it will be secured, and make sure that it is handled properly. Thank you very much for your time. And now we have some time for questions. So,
Any question at all?
Very nice. Yeah, we got 2 microphones on the floor. I'm floating. Anybody ruminating on some?
I think everything was very clear because.
Yes, yes.
Hi, you mentioned that OT SDK is a popular vector for the APTs. How would one go about enumerating or kind of understanding what SDKs are in an OT environment?
Okay, so the SDK itself is not attractive to the attackers. As widely that the SDK is being used on the device, you might want to take a look and make sure that you are properly know your SDK is being used. This is done by follow the SBOM from the vendors that you are using to apply in your facility, and to make sure that when there is updates and firmware updates, you make sure that you follow and update those devices to make sure that if some bad use of a protocol being executed or catch on the wild, you have the protection you needed. It's answer your question?
Any others? We got another?
So while you guys were reverse engineering the sort of PLC loading and stuff like that, it seems like you found a pretty filthy vulnerability like right away. I don't know if you guys have looked at the rest of the code base there as far as how worried people should be about the actual PLC code implementation there.
Yeah, okay. We didn't find the vulnerabilities right away. It took, I think, the first one we found around half a year later, maybe a little shorter. But like from what I've seen there, the vulnerability mostly falls on the spectrum of connecting to dots or using APIs wrongfully or not like fully understanding how exactly the API should be used. And so I guess if somebody would go over all the API usages and validate those are exactly as they should be used, pretty much the 31 vulnerabilities would be saved. So I guess if we somehow can implement maybe something automatically that does that, it can save a lot of life later, probably.
And about you mentioned that you need to be worried. It's always good to keep in mind that when we show the research, we show the worst case scenario. And most of the time, with the proper takeaways that we just share, most of the attack surface will be reduced dramatically, and it probably will be in minor stuff that need to be handled. But when you make sure that you keep network segmentation and hygiene, the OT environment is supposed to be fine until it's not. But we hope that it won't happen. So.
Forgive me, but is firmware upgrades kind of the inoculation to help address the vulnerability?
Okay, so yeah, but the issue is that sometimes it can take a lot of time to propagate to closed networks. And so you do need probably some solution that can monitor this at offline networks. But yeah, the idea is to update in the end. It will be what will save your PLC.
And was there, in going back to the original part of the code, this was the LD portion of a was it PLC? Because I'm over my ski tips on this, but was it this of the family of the framework?
LD is one programming language.
Yeah.
For
This was
PLCs.
just one kind of branch of a number of them.
Yeah, but eventually we wanted to look at the compiled binary. So programming language is not interesting here because this is the compiled version of the code. So we wrote an example project in LD in STL, but eventually we wanted to see how the compiled binary looks like. So this is what we showed here.
Like the final outcome of all of these languages will be little ARM binary compiled. So what is what we looked at. Yep.
Very nice. Any other questions on the floor? Any more? Well, thank you very much. Very informative, insightful. Guys,